traditional history of doing data science has been done on languages like R or SAS, and there the data sets are limited by the architecture of the tool to generally be within the range of a couple megabytes, 100 megabytes, gigabyte being the upper bound, can't go past a gigabyte. So no one's been doing modeling on larger data sets, so the actual sets that you can find available for this aren't getting that big. That said, a lot of people want to go bigger, and with more data, they're getting better answers. They get more predictive models. There's a long tail distribution on a lot of these data sets. And to predict on the long tail, what music people like, it's all very different. You need a lot more data. So people are looking at bigger data sets. So in our case, we started with the notion that we were going to do some math on big data, and then we built a platform for writing math, and I'll talk about that. But the size and the speed are up here. We're looking at two-dimensional, rectangular normalized tables, so it's not some arbitrary structure. Because of the structure of the data, we get a lot of compression. So I say 2 to 4x better than gzip. That's sort of, pretty good. That's actually pretty darn good. And we can do math on it at memory bandwidth speeds. That's the compressed data size. So it gets a lot of speed out for having it being compressed. And the tables or sizes here are, as I mentioned, anything less than like 1,000 columns wide is sort of instantly quick. And things up to like 10,000 work reasonably well. It starts getting slow around 10,000. At 100,000, you start hitting the limits of what makes sense. We have the loops paralyzed the wrong way. But the length is unlimited. We definitely test on data sets with billions and tens of billions of rows. Okay, so also into this clustering technology, there's the distributed key value storage, DKV. I'll do this one slide and won't talk about it again. Basically, you can do a get and a put, and values will move from one node to another as appropriate. They're always cached, they're always fast. If you do a cache hit, it's like about 100 nanoseconds to go get a value out of the key value store. Follows the Java memory models, has exact consistency. It's kind of unusual. And we can get the speed out as well as the exact consistency because we're not doing an H8, a high availability kind of solution. If a node fails, the whole cluster's dead and you have to reboot the cluster. Now rebooting a cluster takes a few seconds, so it's more like a giant calculator. So don't think of it as a key value store, think of it as a big ass calculator. And if something breaks, you reboot, takes a few seconds, maybe it takes another minute to load your big data back into the cluster, and then you could go compute again. Okay, so let's talk a little bit about the programming style. So the big piece of the work here is coming up with a programming style that sort of average programmers can write to that will run distributed, parallel, and fast, right? So you have to do something useful here. So the main paradigm is MapReduce. So it's not Hadoop's MapReduce, but it's sort of a theoretically clean MapReduce, where a map takes something from type A, moves it to type B, right? Does a transformation on it. Where the input for type A is generally both a big data and a small data piece. And the big data is the stuff we hold in memory to do the data sets on, right? So it's distributed data. Not every node has all the data, obviously. And so this is the billions and billions of pieces of data you want to do something with. The other piece is a small data piece, and the word POJO out to the right there stands for plain old Java object. Anything you can jam in a Java object is part of your small data. So a lot of things happen in there that are sort of initial conditions and constants that are part of the calculation that you have to just carry along for everyone to have access to. And so you could jam whatever you want into a piece of Java, into a Java object, and it'll be part of the computation for the map. And then a reduction takes two Bs and makes one B, and there's two kinds of outputs here. There's a small output and a big output. The big output has to be in place on the same node, on the same machine, because it's too big to fit on one node. So if I have a data set that I'm running on 10 nodes, and each node's got 100 gigabytes, so I have a terabyte data set, and I do a filter that filters out 1% of the outliers and keeps 99%, I essentially doubled my data set size. The answer is too big to fit on one node. The answer has to be distributed again. So there's a big data output as well as a big data input notion. And then there's a small data result, which again, anything you can put in a plain old Java object, and that's usually some sort of reduction, summation result. I've gathered up some information, averages and means and standard deviations of data sets and correlations between columns or whatever kind of interesting stuff I want to compute. And for both of these, the main notion of coding here, and I'll show some examples in a minute, is to override what we call Mr. Task, which is MapReduce task, which is just a plain old Java object. And I'll show some coding styles here in a bit, but it's a fairly straightforward model to code. So here's like the simplest possible example. I say new Mr. Task. At the bottom, I say do all on some data set. So data is some pointer I have to a distributed data that's thrown around the cluster. And in this case, he's going to take one column of data and compute the sum of squares. And I write, this code, and it's going to run the same speed as a Fortran compiler will do it. But I don't have to do any other work to make it run distributed. So that's sort of the key notion here is I can write something fairly simple and have it go fast. So we get more complicated stuff. Here, the map is from type A to B. The type A is a pair of doubles. And then type B is the output, is actually the linear regression pass number 1, which is 3 sums, sums and sums of squares. So that's my input, my output. And the map takes the input, which is the big data, and has produced something in the this pointer in the Java language, right? So it's the self pointer. And the reduction is taking 2 such things and folds them together. So out of this fairly straightforward thing, I have what I need to run the first pass of a linear regression, and 2 more passes, and I'll have computed a linear regression between some columns. Best fit line curve on 1 billion observations. So here's another example. In this one, I'm just looking at a count of people who pass a filter. And so I have a filter here which says, your age is low and you're male, then maybe you're an at-risk driver. If you're an insurance company and you're going to insure teenage drivers, how many people in your population, you're all state in the United States of America, and you got 100 million customers, what percentage of them are teenage drivers? What percentage of them are you at risk, for insuring? So you can do something like this and get an answer out pretty quick, get a count. So here's a more complicated example. And let me, where did it, oh, I see what I did. Hang on, back up. Yes, okay, fine. So in this example, I'm doing one row at a time. And the data, as I'll show in a minute, is broken up into chunks. Here I'm going to do one chunk of data at a time, where chunk is a sort of a slice out of my billion long row of data. So there's a for loop mixed in here. I got my slides mixed up, that's fine. Okay, so the main thing I'm pulling out here is that I have an append call in the middle, where I'm actually taking people who've passed my filter and appending them. And this is a big data output. This says I'm collecting the young drivers, the young male drivers, as opposed to just counting them. And so the output down at the bottom here, I've made a new vector of the type appendable vec, and I've appended people, and this append operation is happening in parallel, distributed across the cluster, but also in a deterministic order. So I get the results back in the exact order that they showed up in the original data set, despite the fact that it's all done in parallel, and I'm doing a select operation as I go. I run the filter by saying do all, and then I can go use that later for the next step of whatever processing I want to do with this collection of drivers. So here's a different model. Here's a different demo. This piece of code, the key notion here is that I'm going to do stuff single-threaded. There's no locking or synchronization or issues about parallel access. And what I mean by that is that in the map call, I make a new array. Each map call is run by one core at a time, but on a private subset of the data. So if I say new in a map call, only one core has this array of, whatever I'm computing here. It's a histogram of number of cars you have by your age, right? As you get older, you get more cars, generally speaking. So the histogram is being computed by just simply doing a plus plus. Plus plus operations are not atomic. If I was to run this in parallel with a shared array, I would have a race condition, and the plus plus would drop counts left and right. It would be incorrect. Here it's correct because only one core at a time is running with a plus plus on any given array. And I have one map call per chunk of my data. I might have thousands and thousands of chunks. So I have thousands and thousands of car ages arrays, each one holding a piece of the histogram that I want. And so I have to have a reduction to fold them together to get the one final result out of the end. And that's going down here, or I simply have a utility for adding two arrays together an only element. It's the DAC speed or whatever SAC speed. So standard LAS call. I can also have, so here's a reduction. Here's one that's going to count uniques. And the difference with this one is I've made my new call in the constructor instead of in the map. And that makes that hash set shared amongst all maps because I put it in a plain old Java object in the beginning, and then I say do all, and it's passed around the cluster for everyone to use, and everyone's using the same hash set. So if I write to the hash set, it better be race safe internally, which it is because I've picked one of the concurrent hash sets. And so all the maps are actually counting onto the same hash map, actually the same one per every node. Individual nodes in the cluster will have replicated a version of it. So I still end up with one hash set per cluster. And so it's not to have a reduction step to fold them together cross-cluster. But within a single cluster, there'll be just one hash set, and it's a very efficient way to do uniques within a cluster. 30 cores, we'll run 30 threads, we'll split the data in 30 ways, and run across the data, and they'll all pile in the uniques. First guy in will set a hash set, second guy in will see that it's a duplicate because it's a concurrent hash set, and not worry about it. You eventually collect all the uniques in your hash set, and then finally you get at the bottom, you get your uniques out. So you can count all the unique visitors in a URL set, or the unique instances of whatever. So the sort of coding styles here are that you can write sort of whatever you want within a map and reduce call that's Java code with the following sort of caveats. The code's going to run distributed, so you can't take any resources that would be only available on one machine. You can't do any I/O. If I say system.out print, it's going to print on one machine's console, right? Unless I put it in a map, and then it probably prints on every machine's console in parallel across the cluster, and unless I gather those results, it was not actually going to help me anything. Certainly don't do any reading because the data set won't necessarily be all of it on one machine or another, right? So you don't do any I/O. You don't do any machine resource allocation like asking for threads. There's certainly no locks. So I didn't show any locks here. I'm going to run distributed in parallel, but there's no synchronization mentioned. I'm handling that under the hood. It's actually mostly done by Doug Lee's fork join. If you call system exit, you'll shoot one cluster node down without, you'll end that node in the cluster, and the rest of the cluster members will continue to run and fail because they can't reach the member they need to talk to. There's no global variables because global actually means local to one node, not global to the cluster. We have a different way of thinking about data sets you would otherwise use globals for. So small data that you want to be readable by everybody, you put in the Java object, in the constructor. You just build it in the constructor before you call the do all, and it'll be shared around the cluster in the obvious shallow copy kind of way that everyone gets good sharing out of. If you have something you want to write as a small global output, you use the reduction. And the big stuff you have to go back into and out of the big distributed vectors. So does that all kind of make sense? Maybe sort of. So the plus side, the good stuff, is that I can run on billions of rows without any further effort. That I can just say map for I equals 1 to the size of the chunk, do something, and it runs a billion times over, and actually runs at speeds that you get out of like C and Fortran compilers. It's really fast. And that means that I can run a lot. So it's quite common for us to have math algorithms that make 1,000 passes over the data, but a pass takes a few milliseconds. So it's not slow, it's fast. I don't have to think about concurrency. It's a single threaded coding paradigm. It's what it looks like, but all those maps run in parallel. And it's just because you're actually describing code that you're going to work with in a naturally parallel way. Do something for all these data observations. I have data parallelism, and I'm just letting you code directly to the data, just do direct data parallelism. And then the resource management's all handled under the hood by us, and by all accounts, we do a great job. We'll take the stock GC on a 100, 200 gigabyte heap, and there won't be any insane GC pauses. We'll get every now and then you get a few seconds of GC pause, and that's about it. There's no issues with data placement, which is a common problem with clusters. There's no hot block issues or hot locks. Things scale out very well. Okay, so that was what you can do with it. So I'm going to flip over to like how it works. So this is where we get into like clustered computing stuff. And this is the basic paradigm we're going to use is fork and join, which is recursive descent, divide and conquer, right? So I make some new Mr. Task and I say do all. And when I say new, I get a Java object. So on one node in the cluster, somewhere in the world, the cluster's all peer-to-peer, so all the nodes look alike, but pick one. He's going to be the driver. He's going to start the job off. He makes a new Java object. So somewhere in his JVM's heap, he's got some Java object he just made. And you initialize it with whatever conditions you want to have for initial work, and you say do all some pile of data. So then he says, okay, I don't have all the data myself. Some of it's spread around the cluster. So I'm going to tell other members of the cluster to go do the same thing. So he hands a copy of himself to the other members of the cluster. So that Java object serialized on the wire, reinflated on two neighbors, and they tell their two neighbors, and so on. So it's logarithmic in the size of the cluster. You make a copy of this object and you pass it around the cluster. So there's a log in the depth of the cluster to get things rolling. Once you're on a cluster, on a node of the cluster, then the task looks at the data that's local. Not all the data, just what's local, and he says, oh, that's too much, so I'm going to divide and say, you work on this half and you work on that half. And again, they divide and so on and so forth until you have as many tasks as you have data that you've got on a cluster broken down to some sort of chunk notion. And then you run the map call. And so a map call will be run on one core with one Java object, one instance of this replicated task, and it will update in place. You'll mutate the plain old Java object right in itself, and you get a new version of the same object that's been scribbled on, and it has its output results, so the task.b there, but you have lots of them, one per chunk of data. And I'm only showing 4 here, but typically I have many more chunks of data than I have cores, and the fork join framework does all the right load balancing and sharing across threads for me. So the cloning of these objects, they're small typically, and they clone really quick. So it's just a few nanoseconds to make another Java object clone. Bang, 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 bang. You pile them out really fast. You pile them on the work queues, and fork join like peels them off the work queues and spreads the work out. And all the cores like pound through 30 cores, pound through 10,000 chunks of data as fast as it'll go, and you get great load balancing in practice. And when you're done, you have 10,000 output chunks, output tasks. But actually, every time you have 2 output tasks, you do a reduction. So it's eagerly reducing. It doesn't collect all of them till the end, because then you have lots of output results you're hanging on to all at once, and you have a problem with sort of peak memory usage. Instead, every time I have 2 results, I reduce them immediately. So the reductions happen, again, in a logarithmic tree, but in reverse. So these 2 map one, these 2 fold together to make 1, and so on, until I get one Java object that was the same Java object I started with, it turns out, as a top-level instance with my top-level result for one node. And then you do the same thing in reverse across the cluster, or once I have a result, I serialize it and send it to the neighbor in the logarithmic tree that I started with, and the reductions happen node by node going in reverse up the cluster like this, until the final reduction happens back in the original Java instance I started with. I have my answer on the same Java object and say new, make me Java object. And that's where my output comes. So that operation will take a few milliseconds for the network hops to go back and forth, depending on the size of the data I have to serialize. Maybe some tens of milliseconds if I'm serializing megabytes. Plus the time to make a pass through the data, which is again generally measured in milliseconds. Kind of depends on the volume of data you have and the number of cores and the amount of memory bandwidth, but you can get 50 gigabytes a second memory bandwidth speeds on a modern server. So if you have a couple hundred megabytes, it's going to take a few seconds to pound through it all, but that's it. And then you've got your answer back as your top level instance. So does that all make sense on how the flow goes? So once you've done that, you can make another pass. So for small data, like I'll demo on my laptop here, the passes will be done in milliseconds, and I'll pound through lots of them, hundreds. For bigger data, it's going to take a little bit longer, but generally, if I add more nodes in the cluster, I speed up linearly, and it works. Okay, so let's look at the programming API a little more here. The main notion I carry here is that of a distributed vector, distributed array. So it's an array API. It's got an app and a set to access an element, set an element. There's a length. It's not a Java int because it's too big. There's a notion of a is in a. It's a missing element. It's very crucial to data science. So missing means I didn't collect that observation. For whatever reason, that data wasn't available to me. And that changes the mathematics of stuff. So all the data we carry around carries this notion of something that's missing. And of course, a pin just means I have a variable size vectors that I can change on the fly as I go. So I'm looking at a single vector. Conceptually, it's a Java primitive, usually Java double, but I'm going to compress the heck out of it. So under the hood, the compression scheme will do something domain specific, looking at the kind of data that's there and compress it. So often the compression scheme is much more aggressive than a double, but conceptually you can think of it as a double. It's very long, maybe more than what you fit in a Java array, and I can do linear access on it at Fortran speeds, at memory bandwidth speeds. But it's actually distributed because it's too big for one node. So here's I have 4 JVMs, I have 4 heaps I'm showing. Each will carry 1/4 of the data, and so this array is split across the heap this way. I also do some stuff with GC, and what I do is simply store the data in large primitive arrays, which are free to garbage collect. They require no time from the garbage collecting system. So most of my heap is full of big data in big primitive arrays, but I have very few pointers to garbage collect. So a typical GC cycle, typical Youngin cycle is microseconds, literally. And a full GC cycle on a 200 gig heap is a couple of seconds, but I'll see them like once an hour or something. It's actually pretty rare. Of course, I don't usually have one vector, I usually have a lot. And so it's whatever real world data set I'm trying to collect. Here I'm going to show 5, but it could be 5,000. It's however many columns of data that you're working with at one point in time. And this kind of a notion of a data set where you have a large set of observations going down and some named columns going across. We're totally mimicking the R language, which is the sort of the language of choice for doing data science and statistical analysis for the past 30 or 40 years. The top level structure of a list of named columns are just pointers, and you can reorganize them any way you like. You can drop columns and add columns. Often people will make a duplicate of a column and drop the outliers, or find the missing values and replace them with the mean. Something like that. So there's a bunch of games you play. You do a logarithm transform on a column that's got an exponential distribution in an effort to make it more uniform for doing modeling later. You can think of it as a model of a struct of arrays as opposed to an array of structs. Right? But I can reorganize my struct members any way I like, essentially for free, just a quarter change. So the vectors are all aligned in the heaps so that the same rows are on the same physical machine. And that means that I can, when I work a single observation of data, I don't have to cross machine boundaries. The data is all local on that machine. Within these columns, I also break it up into these chunks I was mentioning earlier, or chunks between roughly 1,000 to 1,000,000 elements. And within a chunk, I'll look at the data I have present and choose my compression scheme. So I have about 15, 18 different compression schemes available right now. And that's all done by the system under the hood. But for instance, if the data you're looking at is Boolean, it's just like yes and no. You have cancer or you don't. You're male or you're female. You're in school or you're not in school. Those are bit sets. And so they'll be compressed, stored as a bit set, not as a Java double, right? I can decompress whatever compression scheming I'm using in a couple clock cycles. And almost always I'm memory bandwidth bound. I went to memory to go grab some more data because it's too big to fit in any caches, so it's never in your cache. That go to memory took 300 clock cycles on a modern x86. I had 4 cycles of instruction issue per clock. So I had about 1,200 clock cycles worth of work I can do while I wait for the data to come in from memory. So I can decompress for free. It costs me nothing to in fact, it's slower to run it not compressed because I get, if I have a double versus a bit, I got 64 times as much data I have to move, 64 times as much time spent pulling the data in order to save a few clock cycles to do decompression. It's definitely much faster to run it on the compressed data directly. The chunks are all aligned on the same JVM heap so that one core can grab all the chunks for one data set and work on it all at once so that he can basically look at any row in any order he likes to kind of decide what he's going to do with the math at that time. Also, the data sets are mutable. He can write to them if he wants to, and as long as nobody has conflicting writes, you're going to follow the Java memory model rules, and in fact, it will run it. Again, memory bandwidth speeds if you're busy writing. So that chunk is also my unit of fork join execution work, and one core will do all the rows, and that's 1,000 to 1,000,000 rows is enough to cover the overheads of launching a thread to go do something. That's small enough to give me some good fine-grained data parallelism. And of course, you don't do one chunk at a time. All the cores light up and grab all the chunks at once. And then you use the fork join framework to handle the reduction steps and handle the scheduling of things. So that's sort of the top level view, is that a data frame is something that will sort of be human readable, and it's a collection of these vectors, which themselves are going to be very large. And the vector is a collection of chunks where a vector will span the cluster, but a chunk will not. The chunk is small enough to fit on one JVM heap. So it's 1,000 to 1,000,000 elements, where elements typically in Java double. I'll handle strings, I'll handle UUIDs and timestamps, a couple other types, but the typical notion is it's Java double. So then that's sort of the high level picture. There's a couple different ways to use the system. The common thing people do now is that you don't think about distributed computation at all. That these are data scientists who use a cluster. They're not systems engineers. They don't do clustered computing. So they treat it as a black box calculator that happens to span a bunch of nodes. And they get at it in a couple different ways. The most common one is we have a REST and JSON interface, web interface style thing. And then anytime you can do anything with a URL, you can drive the cluster. So the common thing you do is you drive it with R or Python or the web interface, all of which go through the REST JSON interface. So you can sit down in an R console on your laptop, on your own personal laptop, the same R console you've been doing forever and a day, and you can say, load a data set in R and do something with it. Or you can say, load a data set in the cluster, and then I'm going to do the same thing with it in R, but what I handed back to the R console was a little cookie inside of R that had a pointer to the cluster. And then I say, do some math on this column, that column, whatever the hell. Those get turned into REST commands to the cluster, which does the big data work. So the same workflow you've been doing in R will work on the cluster as well. And you can get these giant data sets while sitting down and with the interactive speeds as your R console. So that's sort of the common way it works. The next layer in is to do what I just showed you, which is to say, you do some math algorithms using this MapReduce coding style. And we have had, like, Cox proportional hazards was done by a mathematician who had never coded in Java before. But he could figure out how the Java works straightforwardly enough to write a fairly sophisticated math algorithm in Java, sort of as his first Java coding experience. It took him about a month, and we had Cox proportional hazards up and running. This is pretty, it's a good indicator that the coding style is working. As well as Java, we have Scala wrappers. So you can do the same game in Scala. And then if you want to go below that, you can get something fancier. The key value store enables us to do fancier graph algorithms, things that are not MapReduce. So the MapReduce works well. Anything that looks like a dense linear algebra style coding thing. But we can do other stuff under the hood. So sort of summary, the most simple Java just works. The parallel distributed reads, writes, and appends all run at the speed you would expect out of like walking through a plain old Java array, but on big data in parallel. Usually we're memory bandwidth limited, and that covers all the, in fact it's faster to be compressed than not, it's kind of unexpected maybe. But what you can write in those map calls, because it's Java code, you can get pretty fancy. And we certainly have some instances where the Java code is running on for thousands and thousands of lines of code, and it just works. So some of the fancier algorithms do a lot of interesting math in there, and it looks like single-threaded Java code. And you can make it look like the math, and it works. So we've been writing distributed big data analytics for machine learning. So deep learning, which is neural nets. Generalized linear modeling. We have the world's fastest GLM by a lot. We can do a billion-row logistical regression in like 4 seconds on a kind of a stock EC2 cluster. You go to Amazon, pay for a 16 node cluster, and you load in a billion rows of data, and 4 seconds later you got a logistic regression. So it's like super fast. Random forest, gradient boosting method, k-means, PCA, generalized low rate modeling. We got a lot of stuff in there. And we test on a regular basis on data sets that are hundreds of gigabytes now, and we've been doing terabyte scale testing in our labs, and that's working well. So 100 plus gigabyte data sets. Okay, that's clustered computing for machine learning. 30 minutes or less. Questions? Yeah.
Could you give some examples of applications with data which are hundreds of thousands of columns?
So, example. So, anything to do with natural language processing. The common thing you do is you give a Boolean vector for each unique word in a document. So then you scan the web for 1 million documents, looking for the words in them, and then somebody wants to ask the question, find me all the documents that have liberal versus right-wing conservative political bent, right? And so somebody has come through and filtered a bunch of documents that look like liberal speakings and some with conservative speakings, and then you analyze the word sets in these two kinds of documents, and then you make a filter for that looks for, like, find me the closest matches on the web of the 1 million documents, and you come back with all the liberal speak and all the right-wing conservative speak stuff. So natural language processing. And then tens of thousands of health and medical. So you have few observations, you have 1,000 people, but you've collected on each person, you've collected 10,000 interesting facts. So your blood pressure and your heart rate and your pulse and your, you've measured your O2 level and your oxygen in your bloodstream, and I don't know, your age and your rank and serum, I don't know what, but the doctors end up with, if they do a medical study, they end up with tens of thousands of things on a person, but generally a few people. Whereas the text analytics do get to the millions. And then there are mostly people I know who go to the millions. So if I look at data sets of different kinds, the data sets that have to do with, like we look at airline flights, like what airline flights are delayed. You got 30 years of airline flights, you got 1 million, or 100 million flights. That data set has about 70 or 100 columns and 100 million long. And the columns are like